Hello everyone, my name is Rama. I'm from the Center for Nanophase Material Sciences at Oak Ridge National Laboratory, and today I'm going to talk to you about rapid measurement of IV curves using complete information acquisition and Bayesian inference methods. Whew, that's a mouthful. So what I'm really going to talk to you today is about how we can improve the acquisition rate of IV curves in scanning probe microscopy. So let's start with the very basics of how we acquire an IV curve using a scanning probe microscope. So for those of you who are unfamiliar with the technique, basically we have a very small cantilever and we have a tip at the end of this cantilever which is electrically conducting, and we apply a voltage to the cantilever. We then bring it into contact with the sample, and then we basically read out the current that flows from the tip to sample, or perhaps vice versa, using a current amplifier. Because the tip is extremely small, these currents are very small, typically in the order of picoamps to nanoamps, and so therefore we need a nice current amplifier that can boost this current to a voltage that we can actually measure. This typically goes to a computer, which allows us to do a readout and a plot. So here, what I've plotted here is an IV curve, or three IV curves, I should say, from an oxide sample captured using an atomic force microscope. So I basically just varied the voltage from minus 0.6 volts through to 0.6 volts in this case, and I captured three different IV curves across the surface of the sample. What you generally want to do, though, is you don't just want to measure one or two IV curves. The whole point of scanning probe microscopy is so that you can spatially correlate different channels of information. So in this case, what generally is done is that you acquire an IV curve at a single point, you then move the tip to a different point, and then you acquire another IV curve, and you basically build up a grid of points on which you have measured IV curves. And the result of this is basically a 3D data set where you have current at different voltages. And so if you map this out, you'll basically be able to plot the current or voltage slices at different, currents at different voltage slices. Of course, this is a very slow process. An IV curve acquisition typically takes a few seconds, perhaps, for one point. And so if you want to capture a very dense grid of points to be able to tell you something about your material and the spatial variations in the resistance, then you need to wait a very long time for your experiment to finish, because each of these IV curves takes a substantial amount of time. And for example, if you want to measure 10,000 IV curves, you're going to be sitting at the microscope for several hours or even several days. This is not what is ideal when you want to get experiments done quickly. Of course, electronic property characterization in nanoscale systems goes back more than 3 decades, pretty much to the birth of scanning tunneling microscopy. It was the first type of spectroscopy that was ever discussed in scanning probe microscopy. And what you would quickly realize, if you go back to the original papers, is that they very quickly were able to determine that if you take the derivative of the IV curve, what that actually gives you is it gives you the local density of states, or the band structure. And so by capturing an IV curve and differentiating it, it tells you a lot about the electronic properties and electronic structure of your material in the case of scanning tunneling microscopy. You can also map, for example, metal insulator transitions that vary across the surface. So you can start to see, for example, metallic islands growing as you reduce your temperature in a manganite sample, as in this case. And if you build some very, very nice STMs with very low noise environments, you can start to investigate phenomena such as quasi-particle scattering. These really require atomic resolution STMs in really low noise environments and very dense IV curve acquisitions. And such measurements can take anywhere from several hours to several days. And so you need to have a very low drift environment and very low noise in order to be able to make the most of this kind of data set, or be able to even capture this kind of data set. So we asked the question, do we really have to wait so long to capture this kind of data? Can we do so at a much faster rate? Is it even possible to do so? So let's try and return to what we are actually measuring here. So in any SPM measurement where we're trying to measure an IV curve, this is the equivalent circuit that you are looking at. You're applying some voltage, typically to the tip or perhaps to the sample. You're measuring some current, and you have a capacitance in your circuit C, which is providing a parasitic influence and providing a parasitic contribution to the measured current I. And what you're really interested in is you're interested in the resistance profile. In other words, the resistance is a function of voltage of your material. And this is a nonlinear resistor in this case. It's not just a constant resistor in almost all cases. And so what you really want is you want to measure this material property R as a function of the applied voltage V. But unfortunately, what you are measuring is basically a combination of the material property and the measuring circuit. So if we write the equation for what I is in this very simple circuit, it's V on R plus C times dV by dt. This is a really simple equation. What we're trying to do is we're trying to eliminate the secondary term in this equation. We're trying to eliminate this particular term. And so we want to try and make this contribution go to 0. And the way that we can do this is basically by making dV by dt go to 0. How do we do that? We basically don't vary the voltage with time. So every time we step the voltage up, we wait a little bit, and then we basically add a delay time so that we're not measuring current here. But what we do is we measure current after some substantial delay. And so in this case, dV by dt is gone to 0. The RC times constant is probably around here, and so we are measuring the steady state current rather than the transient current that comes from the capacitive term. If we do this, we can also average over some time, try and reduce the noise, and so we basically measure the material property. And so this is how a typical IV curve is actually acquired. So here is a conventional IV curve. This is an excitation waveform. So this is basically what we're sending to the tip or the sample in order to measure our IV curve. And you can see the time scale here, it takes about 1 second. And so we had a very silly idea. Go from a typical conventional IV curve waveform on the left, like that's here, and instead we apply a sine wave like this. In this case, our sine wave can be of any frequency, typically, for example, tens to hundreds of hertz. So we can actually measure an IV curve theoretically even as quickly as 5 milliseconds or even as 1 millisecond or even faster if we apply a sine wave as opposed to this conventional waveform on the left. So what happens when we actually do so? Well, let's look at the theory again. Again, here's our equivalent circuit, the same image that you saw previously. And I'm going to invert it. So I'm going to rewrite it such that we're looking at the resistance as a function of voltage. And we're trying to measure, of course, resistance as a function of voltage given some measurements I, and we apply some voltage V to our circuit. So here's the problem. We actually don't know, if we do measure I, we actually don't know what the capacitance C is. So we can't just put in our I and expect to get a resistance out because we don't know what the capacitance term actually is. And the capacitance can also spatially vary on the sample. So this is really a problem for us. It's also hard to do a reference measurement for this. But let's assume that we can do it. There are some methods that you could possibly use to be able to determine what the capacitance is to a pretty good approximation. Okay, so let's assume that we know what this term is. The next problem that we have is that if we have noisy measurements of I, because this is on the denominator, this really means that when you have noise in I, and it's really close to the noise floor, you have a blow up in the noise in R, because of course your measurement is actually on the denominator. And this is a real problem, which means that when you get to lower voltages, you really are uncertain in your resistance. But the problem is that we don't have any error bars, so we can't quantify this uncertainty using our direct inversion method. So that's the third problem. And the fourth problem is really that we are unable to incorporate prior information. So for example, we know that the capacitance has to be positive. We know that the resistance has to be positive or equal to 0 for a superconductor, for example, but it can never be negative. And so if we just use a simple data-driven approach, we can't actually take advantage of our prior information that we already know is true of our system. And so what we decided to do is we decided to change this and use Bayesian inference, because Bayesian inference can solve all of these problems, all 4 of these problems. In order to do this, we talked to Kody Law, and he's our applied mathematician here at Oak Ridge National Laboratory who deals with Bayesian inference. And he looked at this equation and he said, guys, you know what? If we just take resistance and we invert it, so we create a new variable S, which is the inverse of R, we can rewrite this equation, which is linear in S. We can put a Gaussian prior on S, and we can actually solve it exactly for what the coefficients are in order to be able to reconstruct what the resistance is and also infer what the capacitance contribution actually is. The real advantage of this approach is not only, of course, that it's perfectly solvable using the Bayesian inference method, but also that it gives us some quantifiable uncertainty. If our measurements are very noisy and very close to the noise floor, then our measurement uncertainty will go up, and actually the Bayesian inference reconstructions will also have a very large uncertainty in those areas. So I'll show you an example of that as we go on, but it's a really powerful technique, and it was something that was implemented by Kody Law for this case. So let's start with our experimental results. We turned to a ferroelectric sample because These are very nice samples which typically display polarization switching at relatively low voltages. Nevertheless, here is a ferroelectric nanocapacitor sample of lead zirconate titanate. The nanocapacitors are basically made of platinum, and so you have a platinum ferroelectric platinum layer, which makes up your ferroelectric capacitor. And what we are doing here is we are measuring IV curves across a 50 by 50 spatial grid for the points that are on the left in this topography image. On the right-hand side, or on the middle image, sorry, is the current map, which is basically the result of our standard IV curve acquisition at a particular voltage. So this is a voltage slice. What's interesting to note here is that the vast majority of the sample doesn't have much conduction, which is why it's mostly white. But you see that a couple of the capacitors actually have slightly more conduction than the others, which means that these are more leaky, or they have higher levels of conduction than the other capacitors, presumably because of different amounts of defects within them. And if we look at, for example, a single point, in this red point here, this is what the IV curve actually looks like. You can see that there's almost no current at about 5 volts on the positive sweep. But on the negative side, as you get to about -4 volts, you start to have some leakage contribution to the current. But this is actually very, very small, about half a nanoamp at most. So we wanted to try to acquire the same IV curves, but instead of using the standard excitations, we want to use our general mode or fast sine wave type excitations. You should note that the time taken for this measurement is about 2 hours, and our general mode, because we are acquiring 200 times faster, is of course 200 times faster than 2 hours. So in other words, it's about 10 minutes or even less. In this case, here is our comparable waveform. On the left-hand side is our conventional IV curve, and this is our general mode IV curve, where we can basically acquire at much faster rates, at 200 Hertz in this case. So at 200 Hertz, we're able to scan an image of size 256 by 256 pixels and basically acquire 100,000 IV curves in about 17 minutes, and this really is 1,000 times improvement in acquisition speed. I should note also that this is without any loss of spectral resolution or spatial resolution. In fact, it's an increase in spatial resolution. It's not even a loss. So if we look at the raw data, this is what it looks like. What I plotted, for example, 2 different points of IV curves that you capture using the general mode IV curve method. And what you see here in red is the raw data, and you can see that there are some small wiggles or small oscillations. We can filter those out using Fourier filtering, and so the filtered data is in blue for both of these pixels. Okay, so how do our IV curves look like when we use this fast method of acquisition and then use Bayesian inference? And so what I plotted here is 2 examples of IV curves, one on the top which was captured on the ferroelectric capacitor, and one on the bottom which is captured on the bare PZT film. And what you can see here in blue, in dark blue, is our IV curve, which is basically filtered using Fourier filtering. And in the cyan, which is dashed, this is the reconstructed IV curve from the Bayesian inference method. And you can see that in both cases, they overlay very, very nicely, which means that our Bayesian inference has been able to infer the current very well, and is able to infer also the capacitance contribution very well, because if they did not, if the Bayesian inference reconstruction was not very good, then these should not overlay. But because it has, it means that our model is looking pretty accurate. And so we can plot, for example, the IV curves without the capacitance contribution, and that's what's here in both orange and red for the forward and reverse traces. And very interestingly, you see these bumps. These bumps are actually coming from polarization reversal in the nanocapacitors. And if you're actually over the bare film itself, you're not able to see it because the current over the bare film is much smaller, because the contact area is basically given by the AFM tip in that case. And of course, if you have a very small contact area, then the polarization that you're measuring is smaller effectively. And so therefore, the current that is generated from that polarization reversal is typically below femtoamp levels, and so you won't be able to measure that. But on a nanocapacitor, the contact area is much larger, and so you measure much larger currents, and we're able to see these switching currents. Note that we're not able to see the switching currents in the standard IV measurement. We're only able to see them in this general mode IV measurement. And the reason is quite simple. Remember I said that there was a delay time in the standard IV measurement. That delay time is typically on the order of a few hundred microseconds or a few milliseconds or even a millisecond. And that really means that if there are these kind of dynamic phenomena that's occurring on the millisecond timescale, and this is definitely true of polarization reversal in ferroelectric capacitors, then very often you will miss those in the standard IV measurement, but you can capture them in your fast IV measurement because this is a dynamic mode of acquisition. So that's why we call it the general mode of IV acquisition. It really is dynamic. It's not a static measurement, a quasi-static measurement. We can also look at the resistance as a function of the voltage. And so what's plotted here is the resistance as a function of voltage, which is inferred from Bayesian inference method for both reverse and forward traces. And what I plotted is the Bayesian inference values as well as their covariances. So this is basically the standard deviation, plus and minus a standard deviation. And what you see here is that when the standard deviation becomes very, very large, I basically don't plot what the inference is because the inference is uncertain in these cases. The reason for that is quite simple to understand from a physical perspective. If the current is basically near the noise floor, then the resistance can be arbitrarily large. So in that case, we're not sure what the resistance values actually are, but because we have our covariances, we can easily eliminate those points and say that in these regions, we don't have enough data to be able to make a proper determination as to what the resistance value actually is. And we can do this, of course, for forward and reverse traces for both the capacitor and the film. If you look at the film, you can see that it's basically an ohmic-like behavior, and it's basically got a constant resistance to within error, and it doesn't change depending on whether you're forward or reverse. So the IV curves typically overlay each other in this case because we're not able to measure the ferroelectric switching. So what this method proves is that we can indeed use the Bayesian inference method to be able to infer what an IV curve actually looks like, even when we measure at much faster rates than is the norm. So here's an example of what our current looks like from the Bayesian reconstruction. So I showed you previously a current or voltage slice from the standard measurement that's on the right here. And this is the same voltage slice, but it comes from the Bayesian reconstruction using our fast measurement. And you can see some nice overlap. In other words, this capacitor is quite very highly leaky. It has a very large conduction in the negative voltage range. And that's also shown here. For example, you can see these capacitors are pretty much very low in conduction, so they have very low leakage currents, and that's also shown here. The coverage is not exactly one-to-one, but that can easily be explained by tip wear because we performed the standard IV measurement after we performed the general IV measurement. And so some differences do exist, but I think that's basically due to tip wear rather than anything more intrinsic. Okay. In addition to the current, we can also extract the capacitance and we can plot the capacitance. And very interestingly, of course, our capacitance values are larger on the capacitor because capacitance scales with contact area. So this is again why we can't just use a basic reference measurement to subtract the capacitance from the measuring circuit, because the capacitance can vary across the sample. And so because you have your tip sample capacitance which is varying, it's very hard for you to come up with a very nice reference measurement to be able to infer what the capacitance should actually be. We can go further and we can look at what the IV curves actually mean in terms of the polarization that's been switched. And so this is a very basic. The polarization switch is basically proportional to the area of the switching current. So you can basically look at your ears, as it were, and you can subtract the non-switching part of the current. And you can integrate here to be able to determine what the polarization values actually are. And so we have a map of the polarization in both the forward and reverse traces. I don't want to go into deeply into this, but I just want to tell you that this provides a quantitative view of what the polarization is in these ferroelectric nanocapacitors. And this, to my mind, has not been done before. As far as I'm aware, this is the first time that people have actually mapped the polarization at such a small length scale in these types of capacitors. To summarize, I would like to say that all of our analysis tools are actually available on Microscopy. So we use an open file format, we use open source software, and we actually write our own analysis packages, and they're all freely available on GitHub. So I'd highly recommend that you visit our page, Microscopy, on GitHub. And if you are a Python programmer, please do try and contribute to the project. We're always looking for people to contribute to whatever they can. And if you can provide suggestions and feedback, they're very much well appreciated. So with that, so to summarize, I have shown you that we can use general mode IV curve acquisition along with Bayesian inference to greatly enhance the speed of acquisition of IV curves in scanning probe microscopy. Of course, this can be extended to scanning tunneling microscopy. I only showed you an example of atomic force microscopy, but I do think that it can be extended also to areas outside of SPM. We can improve the accuracy of the reconstructions by imposing more physical constraints on the prior. So for example, we can impose that the resistance be positive as well as there be a monotonic function for the resistance as a function of voltage. And because we believe in open science, we have put our analysis package entirely on Microscopy. It's fully open source. Please do view it. Please do contribute to it. We appreciate your feedback, and we definitely appreciate your collaborations. So with that, I'd like to thank you for listening to this broadcast.